In that case, we can move on. This one also has a similar idea. It's called performers, but it's mathematically a little bit more rigorous. But the math, we are not gonna go into much detail here. What are we doing? We are gonna use fast attention via positive orthogonal random features. And they came up with this sequence of words to give you favor plus. So that's, if you hear the name favor plus or performance, we are talking about this paper. Let's recap attention. You have a sequence length, you have the dimension of your representations, you create your query key value, they're matrices, you compute your attention matrix. Notice something here, this is not softmax, this is exponential. You need to divide it by the summation of something, and that sum, you can actually multiply A by a unit vector. It's going to do this summation across the rows for you. And then your attention, you can implement it as a matrix times value, and this is your attention, the entire thing. This is the softmax of Q times K. What is the cost? This is quadratic in sequence length, quadratic in space complexity, because you have to store A. We are going to borrow some ideas from existing literature about positive random features, PRFs. We have this softmax, or you can call it softmax kernel, which is coming out of the exponential function. This is what you have up there, query times value. And for mathematical reasons, this is a mathematical paper. We want the notations to be convenient. You're going to get rid of square root of d. But when you actually implement this on your computer, this is square root of d is really important. So you cannot get rid of it. But on a piece of paper, we are fine. What is the idea of positive random features? This is coming from random matrix theory. You can approximate this kernel by an exponential of a bunch of random vectors. So you keep sampling random vectors from normal distribution, and the expectation with respect to w of this function times another function is going to give you an approximation for your expected value for your SM. This is actually exact if you keep sampling infinitely many w's and do your summation. But if you want to do Monte Carlo sampling, this is going to end up being an approximation. But what is cool here, you are seeing that there is a function here which depends on q only. There is another function here which depends on k. And we saw this idea before. We just saw it in the paper that we covered, transformers or RNNs. This decomposing bivariate function into single variable functions. Okay. There is another representation of that. If this term here doesn't depend on w, this term here doesn't depend on w, the exponential of that term and the other term, you can bring them out of exponential, out of the expectation operation. And then you can merge exponential of w transpose q, w transpose k into a cosine hyperbolic. That's just a definition of cosine hyperbolic. Okay, so far so now you want to estimate SM. You can have two different estimators depending on which representation you're opting for. And these estimators are coming out of doing this sampling using Monte Carlo samples. You don't have infinite budget, you have a few W's that you can sample from. And M is your number of Monte Carlo samples. You can decompose your SM plus into Q plus or phi plus of Q, phi plus of K. What are those? Phi plus is some H and a bunch of F's. These are your W's that you sampled from your normal distribution, W1 up until Wm. You're sampling M of them. But what is H? This is the exponential of negative of the absolute value squared divided by 2. And you see it here. So you see that term here. That's where this function H plus is coming from. The other one is just the exponential, these F plus. So these are the other exponentials. This is Sm plus. You can have Sm hype plus, which is going to use this cosine formulation. Why would you do that? These are estimates to the true softmax kernel. Whenever you have an estimation for something, the first thing that you need to ask, is this an unbiased estimator? The answer is yes. Are these, do they have a high variance, those estimators? The first one has a higher variance compared to the second one, using the cosine hyperbolic. For that one, you need to sample twice more W's your h is gonna come out of the exponential of this negative q squared divided by 2. Now your q is just x. For the hype plus, the first component, you have the exponential of x. The other one is exponential of negative x. And that one is also coming out of the definition of cosine hyperbolic. So far, so good. Why would you call it orthogonal? We know they are random features because these w's are random. Why do you call them orthogonal? Because you can orthogonalize your w's using Gram-Schmidt. What do we have now? Why did we reduce the cost? Now you can generate q prime and v prime. They are equivalent to your q's and v's. They have different dimension here. And your rows are coming out of these phi functions. And your phi could either be phi plus or phi high plus. So it's a generic formulation for both. R is going to be m for Sm plus. It's going to be 2m for Sm high plus because you're sampling twice more. Your attention matrix here, you can rewrite that formula. This is going to be the inverse. There is going to be q prime times k prime times v. But here is a trick. Don't multiply q by k and store it. First multiply k prime by v and then multiply by q prime. And that's why you are going to save some computation and memory. And how much do you save? I think it's better if I show you the figure. This is the usual attention. This is going to be L squared times L times D. The cost of that, there is going to be a for loop on L here. There is going to be another for loop on L here. That's going to be L squared times D. If you do it the other way around, you first multiply K by V. That's going to have order L. There's going to be D of them here. There's going to be R of them here. That's going to be order LRD. And similarly for the next operation. And this is linear in L. This one is quadratic in L. This was for self-attention. What if you want to do the decoder part? That one is a little bit more complex. You need to look at the lower triangular part of your diagonal, including the diagonal. There is going to be q prime times k prime times c. C is now your v and this identity because we need it to compute d. The idea is don't compute q prime, k prime. Do it this way. First compute k prime times your v and the identity. Then do your summation up until the I. And the only change is that here you are not doing your summation to the end. You are not allowed to look into the future. And then multiply by q. And this is why your g's and gps are going to end up being third order tensors. And the idea is called unidirectional and prefix sum. I think I'm going to stop here. Sorry for going 2 minutes over time. For those of you who have questions, I'll be around. And for those of you who want to leave, you can.